Heidi ho there, Algebra 1B. Alright, so today what we're going to do is we are going to cover the last thing in this unit on exponents and radicals, and this is where the radicals come in. Alright, so basically when we're talking about radicals, they're really the same thing as roots, right? So you've probably heard about square roots in the past, right? It's like, oh, it's finding what number multiplied by itself gives you the number that's on the inside. Right? So a square root is actually, it's an inverse exponent of 2, right? So normally, you'd take 2, or actually, let's use 3. You would take 3, and if you give it an exponent of 2, that's 3 times 3, which gives you 9. Right? But when you take the square root of 9, it spits you back to 3. Right? So what's really going on is that, 9 is the same thing as 3 squared, spits you out to 3. It's kind of like undoing this little squared piece. Right? So that little squared piece and taking this square root are like opposites of each other, right? It's like if I had x plus 3 equals something, I need to do minus 3 to cancel it out. Right? So that's kind of what's going on, is that's what an inverse means, is that they cancel each other out mathematically. So when we're taking a look at radicals and square roots in particular, we've got a couple different pieces that we need to talk about. So one of those pieces is this little tiny 2 in the front there. Right? So that 2 is actually called the index. Right? So the index tells you what it is that you're actually taking the root for. Right? So in this case, it's a 2, it's a square root. Right? If it was a 3, it would be called a cube root. If it's a 4, it's called a fourth root, and then you have a fifth root, and so on. Right? You also have this little symbol here, right? This little kind of checkmarky looking thing. Right? So that does not mean that I am verified on Twitter. Right? This little check mark is called the radical. Right? And I like to think that they called it the radical because it kind of looks like a wave crashing over, where it's like, oh man, look at this wave that's crashing, and your little surfer dude on there. It's like radical, something like that. So that's the radical. And then last but not least, we got this chunk on the inside, and this chunk on the inside is called the radicand. C-A-N-D. Right, so we're going to be using these words a little bit here and there, just so that you know what they are, right? You have the index, which is the tiny little number telling you what root you're taking. The radical is the symbol itself, that little check mark with the line after it. And then the radicand is what you're actually doing the root of, right? It's what you're actually doing the radical to, right? So there's this little piece, this little note down here. If the index is blank, it's assumed to be 2, right? So just like those little examples that I did way up at the top of here, right? There are these little invisible 2's there, right? We were assuming that I was taking the square root, right? So if it doesn't have anything there, it's assumed to be a 2. If it has something else, it's just that thing, right? So pretty much all the time, it's just going to be blank, and you're going to have to assume that it's a square root. So when we're evaluating square roots, right, some of them aren't too bad. So for example, 64, right? This might be one that you've kind of run into in the past. So again, what we're trying to do is we're unsquaring, basically. So what we're trying to think of is what number times itself gives us 64, right? So 8 times 8 gives us 64. So 8 is the square root of 64. As for 121, right, that one's a little bit tougher, but you may have run into it in the past. 121 is 11 times 11. So again, if I'm unsquaring it, right, I'm going to end up with just 11. Another way that you can kind of think about it, right, let's take a look back at that first one there. 64 is the same thing as 8 times 8. Well, how do you do? 8 times 8 is the same thing as 8 squared. So again, the square root is unsquaring that to just be 8. Same thing goes for the 121. 121 is 11 squared, right? And if I'm unsquaring that, it brings me back down to 11. Okay. You are going to run into some every now and then where you're going to need to plug them into a calculator because they are not very nice. So the square root of 17.3, right? 17.3 with a little square root is going to come out to about, I'm going to use a little squiggly equal sign because I have to round it, so otherwise I'm going to be writing numbers for actually forever. It's about 4.16, you could call it. Okay. Square root of 13.5, right? If I can get my calculator to work with me. Square root of 13.5 is about 3.67. Right? So hopefully with a little editing magic, I'll be able to pop right into Google Calculator and show you guys how to plug those in if you do run into problems like that where you need it. And hopefully if my editing skills are great, then I'm back on this screen right now. Ooh, it's movie magic. Right? So again, there's this little note down here. Square roots actually have two different answers, one positive and one negative. Right? So the reason for that is because 64 could just be 8 times 8, but it could be negative 8 times negative 8, right? Negative 8 times negative 8 would also give us 64, right? So what I would say is that this is 8 or negative 8. Same thing for the 11s, right? This is 11 or negative 11, right? Same thing for these ones. For sometimes when you're taking a look and say you're using other resources that you find online, never a bad idea, right? What you might find is that they use a slightly different symbol to talk about like positive or negative. They use this little plus or minus sign, right? All that means is that that could be positive 3.67 or negative 3.67. We don't always know, right? But it could be either one in that case, right? And that's okay. Sometimes you can end up with more than one answer in these problems. So what we're going to mostly focus on are the ones where they come out as positives, right? Because, we could just drop a negative in front of it and give the other answer. But, most of the time we're talking about positive answers. So if I'm trying to evaluate these using a calculator, right? Not a bad idea to try these out, if you're unfamiliar with them. Right? But the square root of 16 is going to be 4. The square root of 100 is going to be 10, right? I'm unsquaring those, right? 4 times 4 is what gives me 16. 10 times 10 is what gives me 100. And then we've got this 1/2 power there. So the 1/2 power is a little bit tricky to plug in on calculators. What I might suggest is if you're using that Google calculator that I was hopping to a little bit ago, I might put this in as 16 to the 0.5 power. Right? Remember that 0.5 is the same thing as a half. Right? And this would be 100 to the 0.5 power. Right? Works either way. What you're going to find is that 16 to the 0.5 power is 4, and 100 to the 0.5 power is 10. Movie magic powers, let's see how this goes. All right, so to do a square root on Google Calculator, what you're first going to want to do is go to Google and just type in Google Calculator. You can probably also type in calculator, and I think that'll work just fine as well. All right, so what you'll get is something that looks like this. So the buttons that we're really going to be focusing on are this little radical sign here, and then you also have this little x with a y exponent. Alright, so one of the problems that we were taking a look at on the notes was the square root of 16. So what you're going to do is hit that little square root sign. It'll bring you up into this, and then it's giving you some parentheses. So that's where we're going to put 16 in. Right, if you want to close the parentheses, you can, but it'll do it for you automatically if you just hit enter. And find that the square root of 16 is 4. Right? What we can also do is we can find, I think this was the same problem. Sorry, I'm doing this afterwards. Is that if I take 16 and I raise it to the 1/2 power, right? Something I might have mentioned is that we can put it to the 0.5 power. That also gives us 4, right? So no matter what you have, if you wanted to take the square root of 17.0365, right? Not that I would ever probably ask about that, right? You can do that. It gives you 4.12752952745. So that means that if I take that and I multiplied it by itself, it would give me that answer that I started with, right? That's all there really is to doing it on Google Calculator. If you run into trouble, let me know, or whoever your teacher is know, and we will help you out with how to plug this in, right? Your phone calculator may also be able to do this in a slightly different way. What I would suggest is type in something like how to use iPhone calculator for radicals, right? Or for square roots, right? Or if you have an Android phone, how to use Android calculator for square roots, right? Just something that'll help you figure out how to do that, or you can reach out to us on how to use this Google calculator to do it. All right, so what are we noticing about this square root that we did over on the left, and this 1/2 power that we just took a look at over on the right? Right? What we hopefully see is that they're the same. Right? They are actually the same exact thing that we're doing, right? They're just different ways of writing it out, right? So this is kind of where it relates to some of the stuff we've been doing with exponent laws, right? If you have something to the 1/2 power somehow, what you can do is you can just take a square root. We're not really going to get too much into them, right? But I do want to mention that if you ever had a third root of something, that's the same thing as saying that thing to the 1/3 power. If you ever had a fourth root of something, that's the same as that thing to the 1/4 power, right? And so on. Right? So it's kind of like when you have these fractional exponents, you can turn it into a radical, like we're taking a look at. Right? Like I said, we're not doing too much with these for now, right? It is something that you may run into in the future, so it's not a bad thing to know about at least a little bit. Okay. So something else that we're going to do with radicals is we are going to work on simplifying them. Right? So simplifying radicals is really, a good thing to be able to do because, square root of 27, that's not really all that useful. It's like I have a hard time thinking about what number that's close to. Right? So if we simplify it, right, it makes it into a number that's a little bit easier to think about. So the way that we're going to do that is we're going to factor the radicand, right? Take that thing underneath the radical sign, factor it to its prime factors using a factor tree, right? So we're going to take a look at a factor tree. And then what we need to do after that is we need to make groups of the factors equal to the size of the index and pull that out. Right? So this is definitely one of those things that's a lot easier to see as we're doing than it is to explain in words. So let's just jump right into one. So when I'm trying to simplify this radical, right, I've got 27. So what I'm going to be doing is I'm breaking up 27 using a factor tree. So a factor tree, right, all I'm going to do is I'm just going to start at 27. I'm going to kind of break it down into some branches. What I want to do with each one of those branches is write two numbers that would multiply to give me 27. Right, so I'm thinking about 27. First thing that pops into my head is 3 times 9 would give me 27. Right? Cool. So something to do here, right, is that we just used up that 27. Right? We broke it into a 3 times a 9. So what I can do is I can kind of cross that out. When we're taking a look at these now, right, I still need to keep on going with the factor tree. I am not entirely done. When I'm taking a look at the 3, right, I'm trying to think of things that would multiply to give me 3. So some of you might be thinking like, oh, well, 1 times 3. It's like, yeah, you're not wrong. I could do 1 times 3. But then 1 times 3, right, I still have a 3. I could break that down into 1 times 3, and then 1 times 3, and then over and over and over again. So whenever you're able to break something down into 1 times itself, you don't need to go any further, right? We just leave that as 3. Some of you might also be thinking like, oh, well, Mr. Pug, couldn't we do 2 times 1.5? Technically, those are factors of 3, right? But what we want to do is we want to use whole numbers, right? We don't want anything that needs a 0.5 or like a 0.33333 or a 0.25, right? We want to end up with whole numbers. So this 3 is actually as far as it can go. Right? So the 3 is done. As for the 9, we can still break up 9. Right? So 9 is the same thing as 3 times another 3. Right? And again, I used up the 9. I broke it into its factors. I'm kind of crossing it out, right? Just to kind of help me keep track of what I've done. So we've got a whole bunch of 3's, right? We have 3 3's that we're working with now. Now what we need to do is we are going to simplify this radical. So this is where that second step, where it's like make groups of factors equal to the size of the index and then pull them out, right? This is where that gets a little bit tricky, right? So what we're doing is we're thinking about what the index is. The index here is just 2, Right? It's just like we talked about a little bit ago. If there is no index there, it's assumed we're doing a square root and the index is 2. So because my index is 2, that means that I need to grab groups of the same number, like in groups of 2. So what I've got here is I've got this pair of 3's, right? That is a group of 2 3's. What that's going to mean is that I'm going to pull out a 3. Right? So the only other thing that we have left over is we have this other 3 that didn't have somebody to pair up with, right? So whenever you have a factor that's kind of left over, what's going to happen is that that gets left on the inside of the radical. Right? So the square root of 27 is actually the same thing as 3 square roots of 3. Right? So we turned this from that into there. And again, you might be thinking to yourself like, well, what's the point? What good is that? Right? Why are we simplifying at all? So again, square root of 27 is kind of a weird number to think about. It's like, oh my god, I don't know what that is. Right? But if I turn it into 3 square root of 3, it's like, all right, it's like 3 and then a little bit more, right? It's 3 times this other little piece, right? It makes it a little bit easier to think through what that number might be, right? It's somewhere in the range of 3, right? So that's what we're doing when we're simplifying, right? So we did our factor tree, we pulled things out in groups equal to the size of the index, put those on the outside, right? And then we had whatever's left over on the inside, right? Something to be careful of is that we did make a pair of 3's, right? In the green there, we only took 1 to go on the outside, right? That's the unsquaring piece, right? We went from having 2 3's to just pulling it out and turning it into a single 3, right? So that's what happens when you're pulling things out of the radical, is that it kind of like, if you have 2 of the same thing multiplying, all of a sudden you only have 1 of the same thing. Right? Let's try another one with 60. So again, first things first, I'm going to start off with my factor tree. Right? You can start off a lot of different ways, right? I'm thinking through factors of 60. There's a lot that I could choose. I could start with, actually I'm going to start with 2 times 30, right? Which means I used up the 60. I could do like 6 times 10, I could do 3 times 20, I could do 5 times 12, right? There's a lot of different ways you can do a factor tree, right? As long as your factors are whole numbers and they actually do multiply to give you what you started with, right? So over on the 2 side, right, I'm thinking about things that multiply to give me 2. Well, I could do 1 times 2, and then I could do 1 times 2, right? But again, we kind of fall into that loop. So 2 is actually something that we can stop at as well, just like the 3's were on the last one. So the 2 is all set. For the 30, I can keep on going. I could break 30 into 2 times 15, and we used up the 30. For the 15, I can break that into 3 times 5, and we used up the 15. So this one's actually got a couple more factors here. So now what I've got, right, I can stop at 5 as well, right, because 5 is just 1 times 5, and then 1 times 5 again, and 1 times 5 again, right? So these are our prime factors, right? I can't break these down anymore. So again, I'm taking a look at my index. My index is 2. I need to grab groups that are the same size as the index of the same things, right? So I have a pair of 2's that match, right? So I can take a 2 and put that on the outside. However, this 3 didn't have a buddy to pair up with, and neither did this 5. Right? So that means that both of those are going to have to go on the inside of the radical. So we got a 3, we've got a 5. So something to be careful of here as well is that that's not 2 square roots of 35, right? Because these are factors, the 3 and the 5. So what we have to do is we have to multiply those. And so when I'm getting my final answer for this is actually 2 square roots of 15. All right, that's how we want to go ahead and get our final answer there. Right. Hopefully this doesn't seem so bad, right? We're just kind of making a factor tree, pulling out pairs, right? Because we're doing square roots for all these, and that's about it. Oh, gross. So sometimes the numbers are going to get a little bit larger, right? So here we have 180, right? So again, no particularly wrong way to start, right? What I like to do is if it's an even number, right? I know I can split it by 2, so I'm going to go with 2 and 90. 90 I can split up into 2 times 45, And then I got to think a little bit harder, right? Because 45 is not even. Right? I can also mark these off because I've used those. So 45 is the same thing as, let's use 5 times 9. Right? 5 times 9 gives me 45. I could use 3 and 15 if you like that better. This 9 we can split into a pair of 3's. Right? Now we've used up the 9. Right, so as you can see, these can get pretty big pretty quick for these factor trees, right? So try and keep everything orderly, keep track of your work. So now again, my index is 2. I'm looking for pairs of numbers that are the same, right? So I have a pair of 2's, I have a pair of 3's. So I can take out a 2 and a 3 to go on the outside. The only other thing that I haven't used is this 5. It's all by itself. So that 5 is going to have to go on the inside of our radical left over. So kind of similar to the last one, right? We had a 3 and a 5 left over that we put on the inside of there. This one we've got a 2 and a 3 that we took out. That's not 23. Don't leave it as 23, right? Again, these are factors, right? We were multiplying with these. So this is actually 2 times 3. So what that's going to give me is this is 6 square roots of 5. Right? This is where we want to get to for our final answers. Okay. Let's try another one out. Gross 216. Right? So again, if you run into a number where you're not quite sure what works with it, right, pull up a calculator. Right? I pull up a calculator all the time when I'm doing these, especially with numbers that are kind of weird like this. What I like to do is, just say like, all right, can I divide this evenly by 2? Right? 216 does get divided evenly by 2. Turns into 2 and 108. Sweet. I know I can stop with the 2. 108. Let's see if I can divide it by 2. Sure can. Turns into 2 and 54. Right? If I can divide 54 by 2, right? 54 does get divided by 2, turns into 27. Right? And again, you might notice that my factor tree is creeping real close to the next problem there already. Right, so I'm going to have to go a little bit sideways. 27, I can't divide by 2, but if I check it, I can divide it by 3. It goes into 3 and 9. Right? I know I can stop with the 3. The 9 can go into 3 times 3. Right? So, sorry that mine's a little bit of a mess here. Right? When you're doing these out on paper, right, again, try and give yourself some space underneath to show the entire factor tree there, right? Otherwise, it can get a little bit messy like mine up there, right? But I'm going to try my best to make it all nice. Right? So, again, our index is 2, so I'm looking for pairs. I need groups that are size 2 to be able to take anything out. So I've got this pair of 2's, and I can also grab a pair of 3's. Right? So that means we're going to have a 2 and a 3 on the outside. But then there's another 2 and another 3 that were left over. Oh, so sad. Right? Those are going to have to go inside the radical. Right? But again, don't leave that as 23 square roots of 23. That is not what we're doing. We're multiplying these things when we have multiple left over. Right? So this is 2 times 3 gives us 6 on the outside. 2 times 3 gives us 6 on the inside. Right, so we have 6 square root of 6. Okay. So what I'm actually going to do is I'm taking a look at how long I've been recording, and I'm going to kind of scooch this along. Right? If you haven't tried this one out, right, try it out. See what you get. Hopefully what you get is you get that it equals 12. Right? What you're going to find is that everything makes a pair, and everything gets to come out and multiply together to give you 12. Right? You should end up with a 2 times a 2 times a 3. Right? And there won't be anything left on the inside of the radical, so you don't need it. Okay. So the ones that I wanted to make sure we get to before I completely lose everything, right, is that we need to take a look at what's going on when we've got variables in there. So there are a couple different ways you could approach these, right? The way that I like to do it is to just treat it like anything else that we've been doing. So one way that you can do it is you can split this up, right? You can split this up into the square root of 48 times the square root of x squared times the square root of y squared. right? So I just took each one of those little pieces and broke it up into its own chunk, right? And that's something that we can do. So then I'm going to approach 48 the same way I would normally. I'm doing a factor tree there. It's 2 and 24. Right? 24 is 2 times 12. 12 is 3 times 4. And then 4 is just 2 times 2. Right? So again, our index is 2. I'm looking for pairs that are the same. So I've got 2 different pairs of 2's. And I've got a 3 that's left over. Right, so we're not going to jump into taking care of that quite yet. What I want to do first is I want to deal with the variables. So the variables are pretty similar to what we were just doing, right? So if I think about what multiplies to give me x squared, it's just x times x, right? So I can break that up into a pair of x's. Right, cool. I can't break those up anymore, but that's fine because we have a pair of x's that we could take, right? So we can take out an x. Same deal for the y's. If I had y squared, that's y times y. That's a pair of y's. Seems good enough to me. Okay. So then as I'm approaching my final answer, what I need to be doing is I'm taking out a 2, another 2, an x, and a y, and then I've got a 3 that's left over on the inside. Okay. And again, everything that's on the outside there in green, that's all multiplying each other. Right, so that's 2 times x times y, which we can kind of smush together and simplify to be 4xy, with that square root of 3 hanging on the end there. Okay. So again, this is where we want to get to. We want to go through all that simplifying to get to that final answer. Okay. 2 left. Oh my gosh, we're almost there. Right. So for this one, same kind of idea. I'm going to break it up into the square root of 98 times the square root of x squared times the square root of y times the square root of z squared. Okay. So for 98, again, it's never a bad idea to use a calculator to help you out with these. 98 can be divided by 2. It'll go into 49. 49 can get split up into 7 times 7. Okay. So again, my index is 2. I have a pair of 7's. I've got this 2 left over. Okay. As for x squared, right, same as the last one. Right, we can break that up into x times x. Gives us a pair of x's that we can use. So then this y is a little bit different. Right? This y is just y. Right? We can't really like break it up at all. So that y, unfortunately, doesn't have anybody to pair up with. Right? There's nothing we can do to break that down anymore. As for the z's, right, we can break that up into z times z, which means that we have a pair of them. Okay. So again, what I'm doing is I'm taking out all the things that should go on the outside. So I had a pair of 7's, I'm going to grab a 7. I had a pair of x's, I'm grabbing an x. I had a pair of z's, I'm going to grab a z. Right. The other part, the pieces that are left over on the inside of the radical, are the 2 and the y. Right. Thankfully for us, right, this one's already simplified. We didn't need to do anything else to it because there's no multiplying that needs to be done with some numbers or whatever. Right. So 7xz square roots of 2y. Ooh, gross. Right. Last but not least, we're simplifying this one. Okay, so this one's a little bit funky because we've got that -6 that's starting on the outside of the problem. Right. So something to be careful of is that -6 is already outside. Right. So when we're approaching our final answer, that's going to be on the outside with whatever else we take out. Right, so we don't want to forget that. As for the rest of this, right, I'm going to put down that -6 again just to kind of keep track of it. We've got the square root of 32. We've got the square root of x to the third. We've got the square root of y to the fourth. And we've got the square root of z. Okay. So again, keeping track of this -6, that is going to end up on the outside when we get there. Right. As for 32, we're breaking that up. That's 2 times 16. Right. 16 is the same thing as 4 times 4. Each of these 4's can get broken down into double 2's. Right? So again, I'm taking a look at what I can pull out from each of these. Right? So I've got this pair of 2's, I've got another pair of 2's, and then I've got a 2 that's kind of left over there. Alright, so that's everything for the numbers. For x to the third, right, we're thinking about what times what gives you x to the third. So there's a little bit of a trick that you can do with these ones with the variables, right? X to the third is just 3 x's all multiplied together. So why don't we just break it up into those 3 x's? Right? So we're kind of breaking the rules on our factor tree that we've been using so far, but that's okay because we know that that is going to give us x to the third, so it's okay to do that. So what I've got here is I've got a pair of x's, and then I've got one that's still left over. Right? You can do kind of the same thing for y to the fourth. We've got 4 different y's that all multiply together to give us that y to the fourth. And so when I'm grabbing the pairs of these, I've got one pair and a second pair of those y's. As for z, right, unfortunately, nothing going on there, right? So that's going to have to just kind of be on its own on the inside. Oh boy, what a mess does this look like, right? So again, just go through it one little piece at a time. Right? Take a look at the green stuff, or the stuff that you've circled and taken out the pairs of. So I've got a -6 that goes on the outside. I've also got a 2 and then another 2, right? Because I had 2 different pairs of those 2's. Right? I have an x, and I had 2 pairs of y's. On the inside of the radical, we just got everything that was in purple, or that I put in purple. You can put a box around it, whatever helps you kind of keep track. We have a 2, an x, and a z that stay on the inside. Right? So this answer is not -622. Right? Again, remember that what we're doing is we're actually multiplying all these things on the outside, technically all those things on the inside as well. Right? So if I do -6 times 2 and then times 2 again, what that's going to do is it's going to give me -24. The x is doing its own thing, and then y times y gives me y squared. Right? On the inside, we've still got 2xz all left over. Right, so this final answer, this monstrosity, is what we're looking for here. Okay. So that's as much as we're going to do with radicals. Be sure to check on Google Classroom, and please reach out to your teacher if you have any questions. Right? We're here to help you out, and I will see you next time.